Hey everybody, thanks for coming. I appreciate everybody coming to the after lunch slot. It's always a risky one because it's pretty full, but everybody else is pretty full and ready to nap, you know. But I hopefully we have a pretty fun presentation in store for you. So today I'm going to be talking about connecting, managing, observing, and securing microservices, and that's a big mouthful. And obviously, any single one of those topics is more than enough for an hour-long talk. So we're going to be doing kind of a whirlwind tour of some of the problem space, the shape of some of the solutions to help connect, manage, observe, and secure services, and then we're going to do a deep dive into Istio itself, which is the particular service mesh that I work on. So just a little bit about me, as she said, I'm one of the core contributors to Istio. Just left to help start a company that's building on top of the project now. And before that, I worked on the project at Google. And like I said, so our high-level agenda, what is the problem? What's the shape of the solution? What are some service meshes that are around that you could use today? And we'll talk a little bit about maybe when one might be more appropriate than another. And then we'll do the deep dive into Istio itself. And in the end, we'll have a nice demo to show some of the functionality that I'm talking about. So this is kind of the motivating problem statement for a lot of for service meshes in general and for a lot of technology that's cloud native today. Our shift to a modern architecture leaves us unable to connect, monitor, manage, or secure. That's the fundamental problem. And so what do I mean by this modern distributed architecture? We mean that we're moving away from monoliths and into services. So there's a lot more points of contact. Whereas before, with a monolith, I might have one or two front doors to get into the system. When I have a set of services, there's doors everywhere into various things. We are deploying them into more dynamic environments. This is both a really good thing and a very painful thing. So these dynamic, fluid scaling environments that cloud providers can give us are incredible. If you were at the talk that was in the ballroom, I guess 2 before mine, that was a perfect intro. Andrew talked about a lot of the challenges of building microservices at scale. And these dynamic environments are a key piece of that. Things like Kubernetes and Mesos and Nomad and other orchestrators let you take use of this flexible capacity, but the problem is you have to architect your entire system around this change that's now introduced. With old style architectures, I worked for an oil pipeline, and we ran 5 services. We had a service-oriented architecture, but I could walk into our server room and I could point to each of the servers that ran our services, right? And that doesn't work when compute scales. You can't go point to the box that runs it. And then the final piece of this, and in my opinion, this is actually the thing that causes the most developer pain, is that our applications are now composed with the network. And the network is really the glue that sticks our applications together. Whereas before, in the world of microservices, in the world of monoliths, we maybe had one process, one giant binary that we could debug through. And really, this is a failure of tooling. And this is a large part of the reason, in my opinion, that it's so hard to move to microservice-based architectures, because the tools that we're used to using to diagnose problems really don't apply in the same way, because they don't know how to navigate the network. How do I trace a request across a set of 10 services that's hard to do? How do I trace a call through 10 processes on a single machine is hard enough today with our tooling. And now you make them distributed, and it's an incredible amount of complexity to add. But we need that, we have to take on that complexity so that we can increase our velocity, move faster, and actually ship features, right? So we have to take on that pain to achieve our business goals. So what exactly are the things that I'm talking about when I say connect, manage, monitor, and secure? When we talk about connections and really, we want to make an application developer not think about the network. And that's really hard when now the network is the thing that glues all of your application together, right? And today, if you go and look at services, you'll see a lot of patterns, like who has written a for loop to do retries? Yeah. So who has gotten it wrong and then DOSed another service? Yeah. Fixing that is a pain, right? Because you have to go redeploy your code, and redeploying code is risky and hard. That's never a good thing. So we want things like resiliency, things like retry, circuit breaking, timeouts. I want to do lame ducking. I want to not talk to a backend that's giving me bad responses. And really, I shouldn't have to build that into my application. Second big piece of connectivity is service discovery. How do I even know the things that I'm talking to and where they live? And today there's solutions like DNS that are widely used that come with a lot of problems. Like, again, because we have this dynamic environment, DNS caches are kind of our enemy, right? How many people have had problems with DNS caching that results in requests going to bad services that should be out of rotation, right? And that can be hard to fix. And similarly, we want load balancing everywhere, because that's really a key to building a robust and resilient system, is being able to shift load easily. And ideally, we would like our load balancing to be client-side. I would like my clients to be smart enough to be able to pick the right destination, because that means that I can have more efficient network topologies, right? If I have to run a middle proxy that does load balancing, it means that it becomes a point in my network where all this traffic has to flow through. And I would really like to keep traffic point to point, where I can keep nice, simple, efficient networks if I can. And so client-side load balancing is a really valuable tool to help with that. Next, we want to do monitoring. This is just what's going on. This gets really to the heart of where I think most of our developer pain is today, which is I have this thing, I have this system, and it's got all these moving parts. What's it doing? And there we need metrics and we need logs, and ideally we want traces too, so that we can actually look at the path of any particular request through our system. And it's not enough just to have metrics and logging. You really need consistent metrics and logging with similar dimensions, with the same semantics for those dimensions everywhere. Because when we have metrics, for example, that are ad hoc per service, it becomes impossible to build a higher level system on top of those metrics. If you use something like a service mesh that can give uniform metrics everywhere, it becomes possible to do things like build alerting on top of those predefined metrics that your entire organization can use. Hey, I'm spinning up a new service. I need to wire up alerts for it. You go, oh, cool, here's the templates already. Here we already have our metrics, you're ready to go. And it really reduces the effort required to spin up new services, the effort required to monitor existing ones. This is one of the key features of a service mesh that we'll come back to, which is just this consistency because a different system is handling these core requirements rather than every individual application doing it. We want to be able to manage the traffic in our system. And we want to manage not just where it goes, where it gets routed to, but how it does that. And really, we want to be able to apply policy to that traffic. I want to be able to look at L7 attributes of a request and decide whether or not my application is going to serve that request or not. And there's a ton of different use cases there. So you can think about maybe some API gateway use cases around things like quoting, rate limiting, auth. You can even phrase auth-z, is this service allowed to talk to another service, is a perfect example of policy that applies to an entire fleet that you can use a service mesh to help you implement. And when I talk about traffic control, a lot of the industry today does L4 load balancing and L4 traffic control, right? So we really want to move that up to be application aware. I want to be able to make load balancing decisions based on application load, on the health of my actual service, not necessarily how much CPU or RAM or whatever it's using, because those may or may not actually be correlated depending on what my use case is. And then a final big key piece that we need now, and this gets back to some of this decomposing of the monolith into individual pieces. Security becomes a lot harder, right? So before I had typically I would have one entry point into my monolith, and we can lock down and firewall everything else, and network traffic is locked down, and I can apply network policies at L3 and L4 to make sure that things can't talk to each other that should. The problem is, all of that is focused on the network identity of a workload, right? What is the IP port pair? What is the machine that's running it? That's what all of our network security is used to dealing with. Except that I just said, hey, we're in this new dynamic environment where things change all the time. And that IP and port that's hosting one application may not be hosting it the next. That's a lot for existing networking tooling to keep up with, right? If we look at some of the early CNI implementations in Kubernetes as an example, they suffered all kinds of problems with crashing kernels and that kind of thing because it was doing IP tables to update which hosts on the network were allowed to talk to which other ones. And it's really, that was kind of an abuse of that system to provide a valuable feature set. And since then, a lot of CNI plugins have moved away from that model. But fundamentally, a lot of the network level tooling that we're used to dealing with is not built to cope with the higher rate of change of applications today. So we want to be able to assign an identity that is tied to the application, not to the host, the thing that's running on the network. I want my identity and I want the policy that I write about what two services are allowed to talk to each other, for example, to be in terms of the services and not in terms of the IP address that happens to host that service right now. And with the goal of moving away from that reachability as authorization model, right? There's the kind of in vogue today is the zero trust networks and Google's Beyond Corp. That's kind of the stuff that I'm talking about here, where we can start to move identity out of the network and into some higher level construct that's tied to an application. So what is a service? So the goal of a service mesh is to move those 4 key areas out of your applications, out of thick frameworks, and into something else. And that something else depends on which implementation you pick. A common service mesh today that people use is just Envoy proxies, right? So we write up some config for how Envoy is going to proxy for my service, and we put an Envoy beside every instance. And you can get a lot of the traffic control, you can get a lot of the resiliency features that I talked about, the telemetry out of that system. You could do something like Linkerd, which is, again, another service mesh that works in the same similar way to what Envoy does now, where you put a proxy beside every single workload, it intercepts all the network traffic, and allows you to provide this feature set. And we'll go into depth about how that architecture works and how those things happen. And then Istio is a third service mesh that provides these features that I talked about. One of the other key goals that I didn't talk about in those 4 are the consistency, right? I want metrics, I want security, I want policy, all of those, that category, each of those 4 categories, I want to be consistent across all of my services. I want retry policy to be consistent, all of that. I would like to be able to control it in one place. And this is a key enabler for velocity. When we add in a service mesh, we can delegate another team to handle a lot of these cross-cutting concerns and move them out of the realm of concern of an application developer. So a single central team can do things like manage the traffic health and the network health of your infrastructure, and individual developers don't need to worry about that. It's a huge force multiplier. Central control is a huge force multiplier to let an organization do more by moving things out of the view of developers. And then finally, another key feature of all of these systems are fast to change. Change on the order of config updates, not binary pushes. And that's a really, really key feature just for that DOS use case that I talked about, right? I have on multiple occasions DOSed another service with a bad retry loop. It's really nice to be able to push config to change that and not have to go get a release in and cut a new binary, right? So Istio is a platform that does that. It is a service mesh that implements a lot of this capability. And so let's talk about kind of in detail how it works. So this is going to be our mental model. It's about as simple as it can be. A just wants to call B over the network. We don't really have to care what. It can be an HTTP REST request. It could be a TCP bundle over TLS. It really doesn't matter. It's just a network call. If it's a protocol that we can understand, like HTTP, for example, then we can get more interesting data about it to show the user. And I'm going to demo a lot of this stuff. I'm going to demo a lot of the telemetry and that kind of thing at the end of the talk, and we'll get to see some of what I'm talking about. But this is just our model. So how do we start to build this kind of mesh to get this functionality that I've talked about? The first thing that we're going to do is put a proxy beside every single workload that's deployed in our system. We call this a sidecar proxy. Istio uses Envoy as its proxy of choice. Envoy was specifically built with this use case in mind, right? So if we think about like a traditional Nginx that we use for load balancing in our system, it has a very different set of requirements than a proxy that we're going to put beside every single application. It's a lot bigger. The rate of change is a lot slower. You're handling substantially more traffic, typically. It's not. You want to make a different set of trade-offs when we're building in this sidecar style model. We want a lighter weight proxy. Keeping the footprint small becomes very important. We want it to be highly dynamic because again, that's one of the big requirements of the system that we're deploying into is that things change quickly. We need to be able to update the configuration of our proxies very quickly as well. And so Envoy was built by Matt Klein and the team at Lyft to address these particular use cases. Secondly, then we need to start to get configuration into the system. So Istio has this component called Galley. It's responsible for taking configuration, validating it, and then distributing it to the other Istio components. So we have these sidecars there. They actually need some config to do something, right? In our system, if we just have static sidecars that sit there, it doesn't give us a lot. So we deploy this pilot component of Istio, which is responsible for understanding the topology of our deployment, what's the network look like, and pushing that information into the sidecar so they can actually do routing at runtime. We want to perform policy at runtime. Like I mentioned, we want to be able to do things like service-to-service authentication. I want to do things like rate limiting. Ideally, I might even want to do things like end-user auth in Mixer. So that's one of those things that invariably in every organization winds up being a library that you include, right? How do you handle your end-user credentials? How do you authenticate them? And how do you authorize them for access? Hopefully, all of your services do it the same way. And they probably use a library to do that. This is another key location where, hey, that's logic that we can pull out and into our service mesh. Things that are horizontal that cut across our entire fleet, we can pull into our service mesh, implement at one time. And if I have Mixer here, in this case, doing the auth policy on end user requests, for example, I don't need my application developers to worry about it. And this is one of the other kind of core features of a service mesh as opposed to other approaches to get this functionality, right? Because service meshes are not necessarily new. There's been things like Finagle that have been around for quite a while that Twitter uses. There's Netflix and Hystrix and that family of things. Those are all very service mesh-like libraries and frameworks. The problem is they're all language specific. Using a proxy to implement it and being the network to the application lets you sidestep that language dependency, and so you can provide all this functionality in a language agnostic way. And again, this is one of those things that helps boost developer productivity, right? It becomes one less hurdle to use a new language in your environment, for example, because a lot of the core cross-cutting functionality, which has traditionally been implemented as libraries, can move out and into a language agnostic format. Huge benefit. And then finally, there's a component of Istio called Citadel that's responsible for provisioning workload identity, that L7 identity that's tied to the application. Citadel is responsible for provisioning that at runtime, and that looks like a certificate. It's an X509 cert, and rotating it frequently. So how does our request actually flow through the system, right? So if we go back to the very beginning, A just wants to call B. We've set up all this machinery, these Envoy sidecars. The control plane is running static, and A issues a call to B. So the first thing that happens is that locally, the client-side sidecar traps that request. That can be done in a variety of ways, but so far, Istio typically uses IP tables to do this redirect. And so it traps all the traffic in and out. Envoy then inspects that request. It looks at the metadata, the L7 request. If this is an HTTP call, we'll look at like the header, the host header, sorry, to determine routing. And Envoy then takes this opportunity to make a client-side routing decision and picks the B instance that we're actually going to send the request to. And Pilot ahead of time programmed all this data into the Envoy. So any given Envoy in the context of a request knows all the other endpoints and can make an immediate decision and route. We don't need to do DNS lookups. We're not out of path. You can immediately route. So we pick a B. We forward our call to B. We don't necessarily know that there's a client-side Envoy on the other side, or server-side Envoy in this case. We don't know that there's a sidecar there or not. Part of the goal of the system is to be transparent. But in this case, we do have one that catches it on the other side. Now, receiving, this is where I want to apply policy. So this is actually in request path. I'm going to block. I'm going to go talk to Mixer, and I'm going to say, hey, here's this request that I just got. Here's a bundle of the data about it. Do I let it through or not? Make a decision. And this is the point where you can do things like implement your own auth-z, right? If you're doing things like a header-based token for auth, it's easy enough to pull that out of the request and do authentication and authorization. You can do things like rate limiting here. Again, anything that you might want central control over is a good fit for policy in Istio. And Mixer makes a thumbs up, thumbs down decision. That's really at the end of the day. Envoy says, do I let it through or not? And Mixer just replies with yes, no, and a cache key. So obviously it would be prohibitively expensive to call out to Mixer for every single request that comes into the system, because that doubles the traffic in your system. That's not feasible. And so instead it turns out that a lot of service-to-service communication, and even end-user-to-service communication, it has a lot of properties that make it very cacheable. Typically, any given client has a very high temporal locality. If you're going to access my API, you're probably going to access it a whole bunch in a short amount of time, and then you're going to go away and not come back for a long time. And then you're going to come back and access it a whole bunch. Very amenable to caching, and you can actually see cache hit rates above 90%. So rather than doubling the traffic in your system by making these policy calls, instead you're talking about a much smaller increase, maybe 10%. So Mixer gives a thumbs up. We say, yeah, cool, let the request through. And so the sidecar there will send the request back into the application that's behind it. The application will do whatever business logic it needs to build its response. Maybe that's calling other services down the graph. Maybe it's going to a database. Maybe it just has the answer in hand. But it'll send that response back. And then asynchronously and out of band, both the client and the server-side sidecar will report back telemetry. And that's awesome because it means that we get a complete picture of what happened from the client's perspective and from the server's perspective, which is massive for debugging. It's so frustrating we typically only ever have the server-side metrics. As somebody that's producing a service, I worked on, I always worked on back-end services myself. I always had my server-side metrics. And there's so many times where the problem is either in the middle or on the client. Having a single system that gives us both sides of that is massive for debugging. It's so awesome. So here's a little bit nicer picture of the architecture that we just walked through with all of the components labeled. And again, like I said, Pilot, config to the sidecars, Mixer is for telemetry and for policy, Citadel is for identity, and Galley is for configuring everything. So with that, we're actually going to dive into a demo, and I'm going to just kind of show you some of what I'm talking about with the service mesh. And we'll see some of the telemetry, we'll see some of the traffic control. So let me frame our demo. This is, if anybody has played with Istio before, you've seen the Bookinfo app. It is the canonical test application that we use for Istio. And this is what the deployment looks like. We have a product page that's the UI that renders a book. It calls the details service to get some details about the book. And it calls some version of the reviews service to get a review for that book. Finally, two of the reviews calls the rating service. So this is what we're just going to deploy. I'll just do a kubectl apply in a second. Where we're going with it is we're going to use Istio to split it up and deploy it across clusters. So this is a use case that I've had quite a few different users talk about, which is we need to deploy across availability zones as an HA requirement, for example. That's a pretty frequent one. I need to run in 2 availability zones as an HA setup, and that's a blocker for my merger and acquisition, for example. So what we're going to do is go from this setup to that setup with no errors. We should see 100% 200s the entire time, and it should be seamless to the application. We're not going to touch the applications that are deployed at all. So with luck, it'll go smoothly. Hey, folks in the back, can you read that? So I'm not seeing anybody vigorously shaking no, so I'm gonna hope yes. If not, it's gonna be a little bit, yeah, no? How is that? Better? Not good enough yet? Sorry, as I'm resizing it, we're scrolling through. Close your eyes, you're gonna spoil the demo. Okay. So hopefully large enough to read. If not, just yell again, right and wave at me. And then let me go to my cheat sheet real quick and make sure that I'm set up correctly. So just real quick, so that everybody can see what I'm doing, I'm just going to alias throughout this presentation. I'm going to use KA and KB because I'm going to be typing, and to type kube control in the context is ridiculous. So KA goes to cluster A, KB goes to cluster B. And then let's go ahead and get Istio. Istio I've already installed, actually. So let me. Sorry, you can never type when you're on stage. And so just to prove that I've installed this ahead of time already. So this is just a stock Istio install. This is actually the Istio demo script. One small change that I'll touch on later is I do have a core DNS deployed, and we'll get into that. And KB is the same. So if I grab this, we can see the same. And notice we have just this one external IP address. That's our ingress into the remote cluster, right? So that's our proxy that's running ingress. So let's go ahead and deploy the Bookinfo into cluster A. All right. And so this is just the standard stock Istio Bookinfo deployment. And similarly, sorry. Wouldn't be proof that the demo is live is that something breaks. Sorry. 1 second. I tried to bypass some of my setup. So all I did was just run a little script that went and pulled the IP addresses that we're going to need later for me, and wrote them into some files, including. Oh, I'm sorry. I meant to do this ahead of time, so I apologize, guys. But so it goes. Okay, perfect. Sorry about that. So now let's verify that our product page was actually deployed successfully. Oh no. All right, so we're deployed. We're there. We have our ingress. Sorry about this, guys. Fun debugging. Let me pull up the ingress. Actually, it did work before, I promise. Alrighty, so we're just going to do this by hand to verify. Alrighty, and then we can do the nuclear option, which is just blow up the pod and yay, fun. Oh, fun. So sorry about that. And then there's one more little bit of setup that we're going to do, which is, if I find my script. Well, and I'll dive into, sorry, this is all because I didn't correctly tear down my cluster last time. I'll go into detail about what this is in a second, but I'm just doing this to set up things. We're using this CW tool that we're using is a small little tool that produces Istio config for us. And we'll dive into in detail what it does. But this now gets everything working. All right, so we have Bookinfo with reviews. All right, awesome. We're at the start of the demo now. Oh, man. So let's go ahead and start driving some traffic to the deployment. I'm going to show you some stats in a second. So all I'm going to do is just start a loop that's just curling the website so we get some traffic in the background. And then I'm also going to go ahead and set up Grafana to run. So in the Istio demo deployment, Istio ships with a Grafana dashboard that lets us see all these consistent metrics that I talked about, right? Sorry, one more command. You can tell that this is a fresh demo. This is the first time giving this particular demo. Okay, awesome. This one's not on me. This is the port forward. Ooh, okay. A little bit. Okay, now we get our Grafana dashboards. Woo! Alrighty, so this is the stock Istio dashboard. So if you've looked at Istio before, you would see it. And here we can clearly see the set of services that we've deployed. We can see the small amount of traffic that we're sending to it right now, about 10. And then we can go and look at any individual service that we have deployed. Again, this is the advantage of having these pre-canned metrics that are homogeneous everywhere. I can do things like define one dashboard that plugs into those metrics that provides useful and interesting data like total request volume, the success rate, our latencies, these critical metrics for actually diagnosing the health of a service out of the box without having to add them to the application itself. And we can see both the client side and the server side. We don't have any, or I guess we do in this case. So these dashboards, awesome, free, out of the box. We're now in this state. So let's go ahead and start to migrate things over. So if we're moving to this end destination, Step one is going to be just to migrate details over first. So we'll go incrementally, one service at a time. We'll ship them over. And the big thing that we want to watch, we can actually see our global success rate. This is aggregate any 500 across the entire system. We'll trigger something there. So we expect that to stay at 100 as we do our traffic shifting. And then let's go ahead and start doing that. So the first thing that we're going to do is deploy the detail service into our second cluster. Alrighty, and if we get the service, we see it's deployed. Awesome. Now let's talk about that CW tool that I was going to demo. So Istio gives us the tools in hand to shift this stuff around, basically playing some shell games with how names resolve. The problem is it's the config to write this, to do these kinds of traffic shifts in Istio is super tedious to write. It's exactly the same every single time, but it's multiple config documents that you need to produce together. So this CW tool that we're going to be using, it's called Kottywample, is something that my team built. And all it does is just generate Istio config for a couple different use cases. The reason I'm talking about it now is because in order to generate this config, we need a little bit of auxiliary data. So the first thing that we need is a representation of our clusters. So I mentioned before that we have A and B. Here is our A and B clusters, and in particular, these addresses are those IP addresses of the ingresses that I talked about earlier. Right, so we're going to communicate between our clusters over the internet via their ingress, and we can rely on Istio TLS to keep that secure. Right, so Citadel provisions identities. Those identities are used to do mutual TLS between workloads. So we can over the internet just go in through the ingress, and hey, that's fine. We set up the same root of trust ahead of time, and so the workloads trust each other, and we can just do TLS all the way through. Not need to worry about setting up a VPN or any other kind of complicated setup that we might have to do otherwise. The second thing that we need is a small representation of the service, enough to be able to generate some configuration to talk to it. And the one thing that we really care about, so this is just, here's the name, the product page service, how we call it. The port it listens one, and then this backends bit here lines up with the clusters in A, right? So if I had product page deployed in B, for example, or I just deployed details into B, I can go ahead and add this as a backend. So what I've just said is, whoops, wrong one. So all I'm doing is updating this little model of our details service, and I'm saying, hey, it's deployed both into cluster A and it's deployed into cluster B, and it's the details.default, that default Kubernetes service name. That's the actual address of the service in the cluster. And so now we can go and generate some of that tedious config to wire up our cluster so that this ingress works, details is here, and then we'll wire up some config on A's side to let it know that cluster B exists. So as we saw before, so this time we'll say, hey, generate config, Kottywample generate config for cluster B, and I care about the details service. Cool. So this just spit out a bunch of YAML. Let me pull it over somewhere where we can actually look and see what it does. So there's 3 key pieces of config that we have here. The first is our gateway. How do we actually get into this details service? And this just says, hey, run on the normal Istio gateway and use the details.global name. This is going to be the name I expect a client to call with this global name to ingress. I define routing for that. I say, hey, by the way, at that gateway that we created, if you see these 2 hosts, go ahead and just send it to the details service. Oops, sorry. I had a typo here in my services. I thought I got it. Okay. And then finally, we have a service entry that just says, hey, by the way, see, I didn't save the, there we go. By the way, this service entry, I'm going to define this name, these two names, and just resolve them with to the Kubernetes service, really. So this just is basically playing a shell game, creating a new name for our Kubernetes service. And our application already talks to this name. And the reason that we want to do this, that we want to decouple naming from the Kubernetes names, is it allows us to do things like shift traffic between clusters. The problem is that Kubernetes names are scoped to a cluster, right? And so if I immediately want to begin to do things across clusters, I need some different naming domain where I can't get conflicts. And so that's why we're playing a little bit of a shell game with some of the names here. And we're using this global service rather than the full Kubernetes service name. And that's also why we're running core DNS in our clusters, so that we can resolve these new names that we're creating, right? So let's go ahead and do that. And sorry, let me verify that I actually saved this correctly so we don't wind up with reviews in there like last time. Alrighty, details, details, details everywhere. Ratings, 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 reviews. Okay. Great, so same config that I just walked through, we're just gonna kubectl apply it. We didn't create our namespace. Excellent. So now I can take this, I can prove to you that our ingress works real quick. So I'm going to curl the details service, and I'm going to set that host header. So critically, we told oh, good grief. We have the same problem that we had in the other one. So let's just kill the pod real quick. Oh. Sorry, and again, this is just a little bit of setup. It's not typical that you have to go delete your ingress pod to get config to apply. Alrighty. Great, so we got a 404, which we would expect, because we didn't set our host header. But as soon as we set our host header, suddenly we can do routing normally, and we can get our details. Great. So we have set up this. Now we want to add our key link. And the way that we're going to do that is go update our representation. So I want to move details. I really don't want to model details being in A. I want to shift it over to cluster B. So I'm going to go back to my model of my services. I just deleted it out, and now we're only in cluster B. And we can look at the, and we can see that we actually generate now a different set of config for cluster A, right? So I said, hey, details moved. The config to talk to details is now a little different. It actually points to this IP address for the remote cluster, right? So we say, hey, if you want to resolve that details name, go over to the remote cluster. So we can just go ahead and apply that. Great. And then the last thing we have to do is, you remember that virtual service that I showed you here? This is currently in our cluster, and it says, hey, when you see details, send it to the local service. Clearly, I don't want that anymore, right? Because I just said, hey, no, I want to move it over to the remote. So let's go ahead and delete this virtual service. And this is just some Istio config. And what we'll see here is, if we come and look at our cluster A, we see that there's traffic going in. If we look at cluster B, we see that the only traffic that was my couple curls. What we should see is that when I remove this rule, our traffic flop over. Because right now that rule says keep the traffic local. And then let's delete it in the right namespace. Cool. So we just removed that config from cluster A. So now what we should see is traffic start is A, still 100% success. This should still load. We're still loading and we're seeing reviews. And we see that traffic is actually starting to pick up. So we're on a 5-minute delayed window for our metrics. So we can see the traffic picked up, but our ops per second is still low. And if we go, we can dig into a little bit more detail here, and we can see that in fact, traffic is picking up. So we just actually, and we can go back to our side that's actually serving our UI and see that we did it with actually no errors anywhere. So we didn't drop any connections to anybody. We didn't lose one of the user requests during that flop over. Everything just kind of flowed through the system. So we're running short on time now because it turns out that the demo is a little bit more efficient when it works. So I want to save some time for questions. So I apologize we didn't get to dig in quite as much as I'd wanted to. But hopefully we got to see a little bit of the telemetry out of the box that's pretty useful. And we can see how we can apply pretty cool traffic shifts and make interesting things happen with just changing configuration, right? I didn't have to touch any of those applications. We didn't have to touch any of the code. It was all deployed and running the entire time, and we were able to change it really without the applications noticing. And that's a key feature for that velocity, right? I want my ops team to be able to manage the cluster and my dev team not to have to care. So questions, we got 4 minutes.
So in your example, you were referring that server A called Mixer to apply policies, and you said that that was no penalty you paid per request. Mm-hmm. But then when invoke service B, there is an again and void. So downstream service, they are not always calling Mixer to check enforcement?
So the server side, Envoy will always call. You want policy to be enforced on the server side because you can't trust the client applied policy, right? So we always do it on the server side. Logically, Mixer is called on every single request to a server, but we cache. Does that answer the question? Perfect.
Can you hear me? Yeah. In the instance you showed, is the same instance of Istio actually managing across 2 distinct Kubernetes clusters?
That's a great question. So, and this gets into some of the Istio multi-cluster work. The answer is today what I demoed you does not actually. So these are 2 separate control plane instances with 2 separate config domains. In my opinion, that's actually how you want to run Istio across clusters, right? So it really gets into what you mean by what's a service mesh. The real answer is identity. These workloads can communicate with each other because they share a common identity domain. Because they have that common identity domain, we can establish connections. It doesn't really matter who's configuring that, right? The fundamental piece is that there's communication. And so we can have separate administrative domains. It's still one mesh because we still have one set of identities.
We have one last question. Time for one question.
So every time I make a call, that Mixer is invoked. What keeps it from being the single point of failure?
Yeah, that's a great question. So again, that caching. So there's a couple different things. So envoys are doing caching, right? So you can think of Mixer in some senses as a centralized cache, and then the envoys as kind of leaf cache nodes. So the second piece is that Mixer itself can be horizontally scaled. Right, so there's not any one particular instance of it. There are many instances. I guess the short answer is Mixer can be a single point of failure if you configure things incorrectly. But in terms of actual scaling, it's horizontally scaled, so one instance going down is not going to kill anything. You can push bad policy that might cause a global outage and be a single point of failure. But outside of that, it tends to not be. And in fact, what we've seen and this architecture actually came out of Google. Google has had a system of identical architecture for about the last 4.5 years now. And actually what we've observed is that not only is it not a single point of failure, but it actually boosts the client perceived availability of the backends that it's in front of. because it acts as a distributed cache. And it turns out that it's really, really, really easy to run a distributed cache at high availability, and it's really, really, really hard to run systems that make policy decisions at high availability. So there are definitely failure modes in which it can be a single point of failure, but in practice, we've actually observed it doing just the opposite and increasing the client perceived availability of a backend. And auth is a perfect example, right? So today, your auth call probably goes, every single service should be calling your auth service for every single request. And instead, you can reduce that by a factor of about 10x by having Mixer cache that and have that result reused. And that just works natively with how Mixer functions. It automatically does these caching of decisions.
Great. Thanks a lot. So we are running out of time. Thanks a lot, Zack, for your great talk.